Hello and welcome to this video tutorial for nuclear reactor design. In this video, we are going to be looking at some example questions using the exponential decay formula. First, we will look at the exponential decay formula itself. This formula can be used to represent anything that decays exponentially. This formula can be used for many things, such as activity, mass, and number of neutrons. In this case, the formula is for activity, and says that activity at time t is equal to the initial activity multiplied by e to the power of the negative decay constant multiplied by time. We are going to start with this example here. A sample of mass 1 gram contains two radioactive elements. 20% of the mass is element 1 and 80% of the mass is element 2. The molar mass of element 1 is 25 grams per mole, and for element 2 is 63 grams per mole. The half-life of element 1 is 60 seconds, and the half-life of element 2 is 12.7 hours. We are going to calculate the initial activity of the sample and also calculate the activity of the sample after 63.5 hours. The first step we are going to take is to calculate the mass of each element present. To do this, we multiply the total mass of 1 gram by the percentages given by the question. Next, we are going to calculate the decay constant for each of the elements. Now, to calculate the initial activity, we need to find the number of nuclei initially present for each element. To do this, we take the mass of each element divided by its molar mass multiplied by Avogadro's number. Now we have all the information we need to solve for the initial activity. To find the total initial activity, we need to add up the initial activity of both element 1 and element 2. In a formula, this would look like decay constant for element 1 multiplied by the number of nuclei for element 1 added to the number of nuclei for element 2 multiplied by the decay constant for element 2. After plugging in those values, we get the initial activity is equal to 5.565 times 10 to the 20 becquerels. Next, we will calculate the activity after 63.5 hours has passed. To do this, we will first convert hours into seconds, so 63.5 hours is equal to 228,600 seconds. To calculate the total activity after a certain amount of time has passed, we need to use the exponential decay formula for both element 1 and element 2 and then add them together. After using all of the values in the formula shown, we see that the activity of the sample after 63.5 hours is equal to 3.622812 times 10 to the power 15 becquerels. The next example we will be looking at is, what is the time required for the activity of thorium-234 to diminish to 50% of its initial value? We are then going to redo the calculations for 10% and then 1% of the initial activity. The half-life of thorium-234 is 24.1 days. We will start by calculating the decay constant, which is equal to 0.02876. Now we are going to find the time it takes for the activity to decrease to 50% of the initial value. We are going to say the initial activity is 100 and activity after time t has passed is 50, which is 50% of the initial value. After plugging these values into the exponential decay formula, the equation should look like this. After rearranging and solving for t, we see that 24.1 days must pass for the initial activity to decrease by 50%. This makes sense because it is equal to the half-life for the element. Now we are going to repeat these calculations for 10% of the initial activity and 1% of the initial activity. The steps taken are the exact same. After performing all the calculations, we see that 80.06 days must pass for the activity to drop to 10% of the initial value, and 160.124 days have to pass for the activity to drop to 1% of the initial value. The last question we will be looking at is, what mass of radium-226 will yield the same activity as 1 gram of polonium-210? The half-life of radium-226 is 1,602 years, and the half-life of polonium-210 is 138.4 days. The first step we will take is calculating the decay constant for radium and polonium. The units for half-life used here are days. Next, we will take note that the molar mass for radium is 226 grams per mole, and the molar mass for polonium is 210 grams per mole. Next, we are going to calculate the number of polonium nuclei that are present. This is the same calculation that we did in the second example, and we can see that the answer is 2.8676 times 10 to the 21 nuclei of polonium are present. Next, we will calculate the activity for the polonium using the formula shown here, and the answer for that is equal to 1.4361 times 10 to the 19 becquerels. Now we want to find a mass of radium, which will give equal activity to 1 gram of polonium. To find the mass of radium, we are going to set the activity of the polonium equal to the activity of the radium. By rearranging and solving for the number of nuclei present, we see that 1.217 times 10 to the 25 nuclei of radium are present in a sample that gives equal activity to 1 gram of polonium. By dividing this number by Avogadro's number, then multiplying it by the molar mass for radium, we see that 4,567.41 grams of radium are required to equal the activity of 1 gram of polonium. This will conclude the tutorial.